Hello everyone, and welcome to the inspiring online seminar series of TÜBİTAK Research Institute for Fundamental Sciences, which we organize for national and international audiences. It is my great pleasure and honor to let you know that our today's speaker is Professor Cumrun Vafa, world-renowned scientist from Harvard University. He has kindly accepted our invitation to join us for this seminar and will give a great talk on puzzles to unravel the universe. The talk is part of our mathematical physics and applied mathematics seminar series. Cumrun Vafa is the Hollis Professor of Mathematics and Natural Philosophy in the Physics Department at Harvard University. Born in Iran in 1960, he moved to the United States for higher education, where he received his BS in Maths and Physics from MIT before moving to Princeton University, where he received his Ph.D. in Theoretical Physics. Professor Vafa is world-renowned for his groundbreaking work in string theory and the mathematical technology needed to explore this field. He is one of the founders of duality revolution in string theory, which has reshaped our understanding of the fundamental laws of the universe. Professor Vafa has uncovered mysteries of black holes using topological aspects of string theory and is the founder of F-theory, which is one of the most promising directions in connecting string theory solutions known as the string landscape to particle physics. He initiated the swampland program, which is an active area of research in string theory with deep impact on cosmology, as well as particle phenomenology. Professor Vafa has received numerous prizes and recognition for his work on theoretical physics, including the 2017 Breakthrough Prize in Fundamental Physics, the 2008 Dirac Medal of ICTP, and prizes for his work on mathematical physics from American Mathematical Society, as well as American Physical Society. He's a member of National Academy of Sciences, as well as the American Academy of Arts and Sciences. Puzzles can unravel mysteries of the universe and illustrate the simplicity of physical laws and the elegance of mathematics, says Professor Cumrun Vafa. With this, I want to thank once again Professor Cumrun Vafa for joining us and look forward to his talk. Cumrun, you're welcome to begin your talk, please.
Thank you, Alikram. Thank you for such a generous introduction. It's a great pleasure for me to be able to give a talk here, virtually, even though that's the way it is. Maybe the one good aspect, I guess, for COVID is that I can see you all virtually, at least. Actually, I would like to make a request. If you can make yourself visible, that would be great. I can see faces. I would love to see faces for two reasons. First of all, I'd love to at least get a feeling of normalcy, even though we are in this COVID situation. So seeing faces makes you feel like everything is normal, at least like a classroom or a lecture room or something. That would be grateful if you could do that, if it's not too much of an intrusion into your privacy. Secondly, I'm going to raise questions and puzzles, and I'm going to ask you to raise hands. So the answer yes or no, you'll be raising hands. So therefore, that's how I want to interact with you. So it's going to be a bit more interactive and more fun, I think, if we can do it that way. So let's see how that goes. So usually in science talks, it's not possible to do that, like voting yes or no, but luckily for the puzzles that I have, it's like that. So I can actually use this occasion to get you interact with the audience and be more fun. So without further statement, let me then say that I would love to come to Turkey, actually when things are in a better situation as far as COVID goes, and see you in reality rather than in the virtual world. So let me change my background to make it more suitable to where we are about puzzles. So I now have my puzzle background. So then I'm going to share my screen. Let's see if I can succeed in that. I hope now you can all see my screen. Is that the case? Just raise your hand if that's the case. Yes.
Yes, it's the case.
It's the case. So let's practice. Everybody sees the screen. Raise your hand. Okay, great, fantastic. Okay, so now let me do this. Does everybody see the first part of the slide here? Puzzles to unravel the universe. Great. So so this is the talk I'm going to be giving to you is going to be based on a course that I'm teaching. I've been teaching at Harvard, and actually I'm teaching it even this semester, about the relation between physics and mathematics. More specifically, using physics, using mathematical puzzles as a way to introduce physics ideas. And the ideas, the puzzles are not supposed to be too complicated. They are not supposed to be very difficult math, but they're supposed to illustrate how powerful ideas can emerge even from simple puzzles. So I'm not trying to give it tough puzzles, etc. But more interesting for me is the connection it might have with some physical principles. Because after all, why we are interested in physics is typically the principles themselves, and not some complicated formula, and not some detailed, derivation of this and that, but the general idea of what is it teaching us. And a lot of these are basic pieces of truth, nuggets of truth, that you can see them hidden in the form of puzzles. So it's going to be based on the book that I wrote, which is the book that is the cover pages here, related to the course I've been teaching for the freshmen at Harvard, Puzzles to Unravel the Universe. So let me get started. So, so math and physics have had a beautiful history of interaction over millennia. So many interesting things have happened over thousands of years in the interaction between these two subjects, and it's still continuing. So let's start with some examples from the past. Some of the examples, perhaps let's go back to the Greek mathematicians and philosophers. So they thought math should be at the center of explaining our universe. They thought that symmetries are very interesting and they should somehow be some connections with reality. They understood the importance of symmetries in the context of Platonic solids, and they thought that the 5 Platonic solids are somehow related to the basic ingredients of the universe, which they thought was air, earth, fire, the universe, and water. So they thought that these things are somehow represented by symmetries. So this was the kind of some of the elementary ideas they originally brought to connect math and physics. This continued in different civilizations, Chinese civilization, Indian mathematicians, Islamic scientists, and so forth, continued these traditions. For example, Biruni accurately measured the radius of the Earth by simple geometry arguments, by going on top of the mountain and noticing that if you look at the horizon is not at the same place as the vertical line perpendicular to the vertical line, and by finding that angle and the height of the mountain, he estimated the radius of the Earth to very good accuracy. So simple ideas of geometry already was used. Actually, already Ibn Mu'ad in the 11th century figured out how to compute the height of the atmosphere. We think today that, how can you possibly measure the height of the atmosphere without sending something up there? But actually, 1,000 years ago, by simple ideas, they computed or estimated the height of the atmosphere. And the idea they had was very simple. The Ibn Mu'ad idea was simply that if we are somewhere on the Earth, when there's a sunset, even after the sun sets, when the sun goes down, you still see a part of the blue sky. And it takes a while for you not to see any light, and it gets really dark. It takes a few hours. So by measuring how long it takes for the sunset to go to complete darkness, you get an estimation, because when it's completely dark, the last ray of light gets to the top of the atmosphere. And so from that, how long it takes to do that, and the fact that the sun goes around the Earth, so to speak, once every day, you can figure out the height of the atmosphere, at least the ratio of that to the radius of the Earth. And since you know the radius of the Earth, you can measure the height. So these simple ideas of geometry already began to be interesting for applications to the real world. Then this continued with the traditions of great physicists, Galileo, Newton, who invented calculus to describe the laws of mechanics, and then more mathematicians joining some ideas that later became important. For example, Gauss, that thought perhaps our universe is not Euclidean. And for example, if you go on top of 3 mountains and measure the angles that the light rays make from one mountain to the other, if you look at the other mountain peak, and you measure these angles from each mountain peak, and if you add these angles, he wondered whether that adds up to 180 or not. So these are non-Euclidean geometries, was the question that was in their mind. Maxwell wrote these beautiful equations to capture electricity and magnetism by beautiful equations, and in fact discovered that electromagnetic waves exist, and he conjectured that light is nothing but electric and magnetic fields moving. And these were, underpinning of it was a simple, beautiful, elegant math equations. And Riemannian geometry, which Riemann pioneered and studied, became a way to try to not only describe math, but he actually was thinking of possibly unifying electricity and magnetism with gravity. Now this had to wait, of course, till Einstein came to the forefront, where he used Riemannian geometry in 3 spatial dimension and 1 time dimension. So if you include space and time together, to describe the geometry of space-time. And he wrote his beautiful equations, Einstein's equations, which captures the response of the space-time metric and the distance and the fabric of space with respect to where things are located. And then further down, Kaluza and Klein used Einstein theory by going to higher dimensions, instead of 3 + 1 dimensions, to 4 + 1 dimensions, to try to unify gravity with electromagnetism. So similar ideas of extra dimensions came to fore even early on in the beginning, very close to the beginning of 20th century. So these are some of the examples of the connection between math and physics from just a very brief survey of the past. But my area of research is an area called string theory. And the aim of string theory is to unify fundamental forces and particles into one framework. It aims to describe physics from the smallest, the tiniest scale, a trillionth of the size of an atom, all the way to the size of the universe. And the basic assumption or basic postulate is that fundamental particles are not point-like. They are not like constituting at the point, but they are extended objects like strings. So instead of, for example, quarks inside the nucleus of a proton, you think about each quark himself, like up quarks and down quark, as strings here on the right, which is invisible or too small to see when you're too far from it. So it looks like point particle, but actually if you zoom in, the prediction is that you'll see some extra structure, which shows they are not point-like. And string theory resolved the inconsistency that there is between quantum theory and gravity. And so interactions of strings are naturally described by 2 strings coming together and unifying. And this is called the pair of pants diagram. It looks like a pants. So this underlies all the fundamental interactions in the universe in this form. There's just 2 things joining. It's geometric. Again, you see the power of geometry and how geometry can elegantly describe physical forces. So all the forces comes from this geometric picture as far as string theory is concerned. So it's very simple. Now, this area, string theory, which is my area of research, is very mathematical, and it involves many abstract ideas. And the dimension of space is more than, space and time is more than 3 plus 1. It's 9 plus 1 in some form. And the shape and size of this extra 6 dimensions will affect what we see in our universe. So they are assumed to be tiny in our universe, these extra dimensions, to avoid contradictions. And strings can wrap around these tiny dimensions, and they lead to insights about how the black holes work and how the beginning of the universe worked and all that. So you can think about our universe as big dimensions, some flat directions, and then there are some tiny little things like spaces which are sticking out, and they're so small you couldn't see it. So therefore, these extra dimensions are no contradiction with your everyday life where you see only 3 spatial dimensions, because these other dimensions are tiny, and in everyday experiments, you take an average, kind of. So you don't see, you just see an average in some form. So my aim in this talk is not to go to these highly mathematical ideas, but actually, the highly mathematical ideas that arise in string theory can actually be illustrated by simple ideas. By simple ideas, much simpler ideas, and this is what my point of this talk is. And I'm going to basically present them in the form of puzzles. So the math-physics connection. So the first, I'm going to divide this to various topics. These topics are familiar to you as physicists. How many of you are, I mean, many of you are physicists, I'm assuming, but just want to make sure. How many are physicists? Raise your hand, please. Okay. I'm glad that not everybody raised their hands, because a lot of what I'm going to say assumes you know very little about physics. So with apologies to the experts in the audience, it's going to be, my assumption is that you're not very familiar with string theory, but if you are, which many of you are, please view this as a way to connect to simple ideas in physics using simple puzzles. So let's start with the first puzzle. The first puzzle has to do with symmetry and conservation law. So we have 2 containers. One has a green paint and one has a white paint. We take a glass, we fill it with the green paint, we pour it in the white paint, and take the same amount after we mix this mixture. We take the same amount from the mixture and pour it back into the green container. Okay, to begin with, there was equal amount of volume we started, equal amount of green paint and white. We poured from the green to the white, and then we poured the same amount back after we mixed them from the mixture back to the green. Is that clear to everyone? Yes? Good. Now the question we want to know is, which container has the higher concentration of the other color? In other words, does the green paint have more white in it, or the white one has more green in it? Is the question clear? How many of you think the green has more white? Raise your hand if you think the green container has more white. How many of you think that the white container has more green in it? How many of you think they are equal? Okay, so the majority of you, as you saw, said that the white container has more green. And that is intuitively what most people would say. Why is that? Well, the reason is, when you originally started, you first took it out of the green container and put it into the white. So you got a complete full of green cup and put it in the white, and then you mixed it, and out of only the mixture you put something back. So you didn't put pure white back into green, you brought in some mixture, so you brought some green back to green. So for that reason, many people think that the white has more green. But actually, it turns out they are equal. The amount of white and green are equal. Now, this is completely surprising. But what is even more surprising is that it follows from symmetry and conservation law. So symmetry and conservation law proves this. How does it prove it? Well, so this is how we deconfuse ourselves using symmetries. The reason this happens is the following. You started with equal amount of mass in both ones. Green and the white were equal. you took the certain amount of green and put it in the white and the same amount back to green. So the final and the initial masses are equal. So therefore, what happens is that whatever is missing from one must be somewhere else, must be in the other guy, and vice versa. In other words, just the conservation of the mass will tell you they have to have equal amounts of mixtures. And to see that even better, let's do the following. Let's take these and try to unmix them. Suppose you unmix it. Whatever is missing from the green must be white, and whatever is from the white must be green in such a way that if you swap them, you get back to original volume. So there, of course, they have to be equal in volume. So this shows that certain symmetries here, the symmetry and the fact that things are conserved, just gives you a simple answer, even to something that you intuitively thought it could not be true. So it's powerful. Even though you might think symmetry and conservation is kind of boring, it's not boring, as this example showed. So in fact, you can see this example perhaps better by a following version. You can take a deck of cards and take 10 red cards and 10 black cards, and take 3 of the cards in the red and put it in the black pile, and then shuffle them. And then take 3 cards from this mixture and put it back into the red pile. And then you can also shuffle that. So this is very much like the green and the white one that we talked about. It's just, I'm just now doing in terms of concrete cards, like atoms of the paint, if you think of it that way. So then the question is, does the red pile have more black cards in it, or the black cards have more red in them? Of course, it's exactly the same as the other puzzle. And to see that, you just have to turn them around and look at them. Of course, you have 10 cards to begin with, and you have to end up with 10 cards. So if you are on the left side missing 2 cards, it must be that the red cards are over there, and vice versa. So therefore, if you swap them, you get the same amount of cards. Is that clear? Okay. Now, another example of symmetries and conservation, the symmetry principle, is the example having to do with the objects falling. And this is Aristotle's perspective on it, was that heavier objects fall faster. If you have 2 objects, one is heavier, one lighter, he thought that the heavier one, of course, falls faster. It's intuitively obvious to anyone that this should be the case. Why it's obvious, I don't know, but it's obvious to almost everybody, except the ones who have studied it. But Galileo objected to this, and he said, no, in fact, all objects fall at the same rate. That was one of his major contributions. How did he do it? Well, we are told that he went on the Pisa Tower and dropped stones and see big ones and small ones and see which one falls first. Believe it or not, the scientists at that time did not find this convincing. They said, maybe there's something wrong with your experiment. You have to explain why it's like this, that they fall at the same rate, the heavy and lighter ones. So he had to come up with a theoretical explanation. So today, science is very much experimental, so we don't understand why they would even raise this question. But at his time, they were actually wanting to know, how could it be? How could it be that the heavier objects don't fall faster? So he came up with a brilliant explanation using symmetries. And his symmetry argument was very simple. He said the following. He said, suppose you have 3 bricks that you take it and release it from the same height. Which one will fall first? Well, he argued using symmetry that they fall at the same time, because you started with 3 identical bricks from the identical heights and let it go. Since translational symmetry in the horizontal direction is a symmetry, then they all fall at the same rate. Everybody said, yes, yes, we know this is obvious, but what does it have to do with the question of heavy versus light? He said, well, let's consider moving these bricks around, and let's consider bringing 2 of the bricks closer. Does it change the answer? No. Why? Well, because the same height. It doesn't matter where you put them as long as it's the same height. So everyone agreed this is the same time. Again, all 3 fall at the same rate. He said, it doesn't matter where I put them, right? Horizontally, I move them. They said, no, of course it doesn't matter. It's obvious it shouldn't matter by symmetry. So he said, well, then bring them so close to each other that 2 of them almost touch. And then these 2 things look like one heavier object, and then you just told me that they fall at the same rate. So by symmetry principles, they fall at the same rate. And now these two bricks is twice the mass of the other one. So in this simple way, we kind of portrayed the picture that by symmetry, you can make it obvious that heavier object and the lighter objects fall at the same rate. Again, the power of symmetries. But actually, even though symmetries are fun, breaking them, and in physics, we love to break symmetry, it's called spontaneous symmetry breaking, turns out to be actually much more interesting and much more powerful than having symmetries. So breaking them is more fun. Why is that? Well, let's get some examples. Suppose we have 4 cities in the corners, on the corners of a square. So A, B, C, and D are 4 cities on the corner of a square. And what we want to do is we want to find a highway. Not find a highway, we want to build a highway which connects the 4 cities together. But we want to have the total length of the highway to be minimal because the cost of the construction is too much. So we want to have the shortest possible total length of the highway. But we want to be able to go from every city to every other city. It does not have to be a direct line from every city to every other city. As long as you can get from every city to every other city, we are fine. So the puzzle is to find the shortest highway system. Okay, is the question clear? Yes? Good. Okay, how many of you think this is the answer? Raise your hand. Okay, how many of you think this is the answer? Raise your hand. Okay, how many of you think this is the answer? Raise your hand. Okay, well, so it's not completely clear. And so in fact, if you go by symmetry principles, you might think that, well, this is of course the same as the previous one because we can move it back and forth, but it turns out that the answer is actually this. The shortest highway system connects the A and C together, and then you make a 120-degree angle. So these 3 angles that it makes are all 120-degree angles. And this is the shortest highway system. Why is this strange? Well, the reason this is strange is that it does not respect the symmetries of the square. You see, if you want to go from A to B versus A to C, now it's easier to get from A to C than from A to B, because A to B, even though they are physically at the same distance because it's a square, now the highway system from the highway is longer to get from A to B than from A to C. Is that clear? So we have broken the symmetry. We started the problem by symmetries of a square, but the solution of the shortest highway system does not enjoy the symmetries of the square. So that's a surprise. Indeed, you might say, okay, so interesting. So what does this teach you? Well, it turns out that many of these things have actually been studied in many different contexts. And in fact, even the early Greek philosophers thought about this. So let me explain how did they think about it. You know, these Greek philosophers and mathematicians were very smart. They had already figured out that the Earth is round. And they knew the Earth, they studied the Earth is round basically by looking at the properties of the shadow of a stick, vertical stick. If you put it on the ground, and whether you are on the equator or not, the length of the shadow changed, and they figured out that the Earth is round. They already knew Earth was round. But they thought incorrectly that Earth is not moving. They thought it didn't look like things are moving around them. They said, okay, so it's basically the Earth is a sphere and it's not moving. And they say, wow, why is it a sphere? They said, well, maybe it's a sphere because it's at the center of the universe. So they say, okay, the Earth is at the universe, centers of the universe, and it's not moving, like this picture. So we have the Earth at the center of the universe, and it's not moving. But they say, well, why is it not moving? And then they said, aha, because of symmetry. You see, if the Earth is at the center of the universe, if it picks a direction to move, it breaks the rotational symmetry. So anytime it moves in some direction, if it moved, then it breaks the symmetry. And breaking the symmetry is bad, they said. You don't want to break symmetry. Therefore, Earth is not moving. So their argument that the Earth was not moving was related to symmetry principle. It's a very smart idea, but actually, Aristotle, well, again, back then said, this is not a good argument. So he rejected the argument. He said, that's not a good argument. And the reason it's not a good argument is that suppose you put a person at the middle of a circle full of food. Do you think that person is going to stay in the middle of the circle and not go for the food just because they don't want to break circular symmetry? No way. They're going to break it and go and get the food. They're going to die of hunger if they don't do that. So what Aristotle pointed out with this example is that symmetric situation is not optimal sometimes. You have to break it to get the optimal solution. In this case, getting the food. Is that clear? In fact, even our bodies reflect that fact. Why is that? Well, we live on Earth, and Earth is by and large horizontally symmetric. So if you look around you, 360 degrees on the average, it's all the same. So therefore, if we are made by evolution, our bodies are made by evolution, we should have a 360-degree rotational symmetry. But of course we don't. And in particular, our eyes are in front and not all around us. So we have only eyes in the front. Why is that? Well, spontaneous symmetry breaking, again. Why did nature decide that our eyes should be in the front and not all around? Because it would be a waste of resources. Why is that a waste of resource? Well, just imagine you're at the center of that circle. You want to go towards the food. You just need to know where the food is. So you need the eyes in the front. You don't care about all the eyes all around you. So you go towards the food. So that's why we actually have eyes in the front. So that's actually more efficient to use those resources. So in other words, our bodies reflect the spontaneous symmetry breaking. Now it's almost left-right symmetric and so forth. So it's an approximate symmetry is preserved and so on. But at any rate, those are interesting principles that we are learning from the studies of symmetries. Now, modern applications of symmetry breaking involves Higgs particle and the origin of mass. So, so let me then move on to some unreasonable power of simple mathematics. So this is another example that shows that we have a lot of things that come not just by complicated math, but even almost trivial looking math, simple, very simple math. How does that work? Let me just give you an example. Consider the Earth and take the equator. So this white circle there is the equator. And now wrap a belt around it. So suppose this white circle there is actually a belt wrapping the equator, the circle of the equator. You open it up. So we have now opened the equator into a line. Now what we're going to do is we're going to add 1 meter to it. That green little thing at the end is, let's say it's 1 meter. And then we're going to wrap it again around the Earth. Now, it's not going to wrap tightly around the equator. It's going to stick a little bit outside. Okay? How many of you think that you can pass a piece of paper from under this raised belt? How many of you think you can raise a piece of paper? Raise your hand. So you can push a paper from underneath this belt? Raise your hand. Yeah. How many of you think you can push a mice from under the belt? Raise your hands. How many think you can put a skyscraper under the belt? Raise your hand. Yes, of course, nobody would give the silly answer of skyscraper. But actually, it turns out that it's an easy calculation to show it's actually 16 centimeters. So it's, why is that? Well, if you call this length x, how do we calculate it? Well, the original circumference was 2 pi r, and you add 1 meter to it. So 2 pi r plus 1 should be a new circumference, which is 2 pi times the new radius, which is r plus x. And so if you get 2 pi r's canceled from both sides, you get 2 pi x is 1. So x is 1 over 2 pi, or 16 centimeters. Easy. Is that clear? So everybody says, wow, 16 centimeters. Usually, you would think it should be very tiny because you're just adding 1 little meter to this huge equator. And so it should be very minute. And so the intuition is that it's microscopic, it's atomic or something. But actually, it's 16 centimeters. So you indeed can have a mice also pass under it. But actually, let me ask you the following question. Suppose I pull the belt from one side. Suppose I pull the belt on one side of the Earth, so it's tight on one side and non-tight on the other side. You see what I'm saying? To make it push on one side, so asymmetrically, push it on one side so it's tight around the equator, but pull it on one side. How many of you think you can lift X? X is bigger than 16 centimeters then? Raise your hand. How many of you think you can do this by half a meter or more? Raise your hand. How many people think can do 1 meter? How many think you can do 120 meters? Of course not 120 meters. But it turns out the answer is 121 meters. Okay? Simple math, but shocking result. Now you can go and check it. Just go and check it. So if you add just 1 meter to this belt and you just wrap it around and it's tight all over, except just a little piece, you just pull it out, you get 121 meters. So indeed you can pass a skyscraper from under this. It's remarkable. This is a little bit more advanced math. It involves a little bit of a calculus, so I'll leave it to those who are enthusiastic to check it. But at any rate, it gives you an example that simple ideas can give dramatically unintuitive answers. So the next example I want to tell you is the power of continuity. Continuity is an important principle of mathematics, but actually it's also an important principle of physics. In physics, we have the laws formulated in terms of equations, and equations have continuity properties and continuous solutions. So in physics, things don't jump around. They're smooth, continuous, typically. So continuity turns out to be a powerful principle in mathematics, and I will give you an example of it. Again, let's go back to my favorite situation, Earth and the equator around that circle. And suppose we want to measure the temperature on the equator. So typically, as you go around the equator, the temperature varies over the equator. Could it be that as the temperature varies, that no matter what happens, there are 2 points on the equator opposite to each other, which have exactly the same temperature? Could we have a situation where 2 opposite points have the same temperature? Well, it could be, but the question is there always a pair of points which have the same temperature along opposites relative to the center of the Earth? How many of you think that there always will be 2 points with this property? Raise your hands. How many of you think no, it depends on what the temperature is? Okay, so it's like half-half. It seems like some of you didn't wish to express your opinion, but anyhow, it turns out that there always is such 2 points. So, and this follows from continuity. How do you argue? Well, consider the temperature on the opposite points. If they are equal, you're done, of course. Suppose they are not equal, consider the function, which is the difference of the temperatures on the opposite points. So this function, if it's zero somewhere, you're done. So you want to see if this function ever is zero. If this f of theta is somewhere zero, you're done. Suppose it's not zero at some point. If this point theta angle goes to the opposite angle, if this goes to the opposite angle, f goes to minus itself because it switches which temperature you're looking at. So therefore, if t is positive, if f is positive on this angle, it will become negative on the other one. But if a function is positive and goes to negative, or it's negative and goes to positive because of the property that's antisymmetric, it implies that it has to cross zero by continuity. So continuity of a function f, which in this case is because of the continuity of temperature, which follows from the continuity of physical laws, implies that there always are 2 points which have the same temperature. So from a very simple basic physics fact, namely the continuity of the equation, we learn that there are always 2 temperatures which are the same opposite on the equator. Is that clear? There's a more fancy version of this, which I leave to you as an exercise, that not only there are 2 points which have the same temperature, but there are 2 points on the Earth, not just on the equator, on the Earth, opposite relative to the center of the Earth, which have exactly the same temperature and pressure. It's amazing, you might think, right? If you just opened up the TV and they said today, it happened that at every moment, there were always 2 points opposite relative to the center of the Earth, which had identical temperature and pressure. You might say, wow, what happened? How could it be that? Who arranged that? And it turns out it simply follows from continuity. So continuity already gives you this. The next example is gravitational lensing as another power of the continuity. Gravitational lensing is a beautiful property of Einstein's theory of relativity, general relativity. So Einstein's theory of relativity implies that if you consider the fabric of space-time, it is curved. And therefore, the light which follows the shortest path, or geodesics, will not be straight. There will be some paths that it would take. And these paths will be, in principle, not straight line. And so you get multiple paths from one place to another, and you get multiple images. And therefore, you can have 2 or 3 different things coming at the same time from the same object. So you think that they're different objects, but they're the same. And this phenomena is called gravitational lensing. So for example, if you look at this picture, in this picture, there are the same objects have repeated a number of times. In particular, there are 5, these blue circles are the same quasar, and these 3 orange circles are the same galaxy. You might think that they're different, but they're actually identical the same. Is that clear? So this is quite surprising that you can see multiple images. But it turns out that this is the fact that you see this number of images is actually explainable using Einstein theory in the following property. The number of gravitational images is always odd. There are always an odd number of images, unless you block them. So let's not block the images. Suppose all the light is coming through, nobody's blocking them. So if you don't block the light, there are always an odd number of images, and always less than half of them, just less than half of the images are reflection. They are not right side up, they're reflected. Now, you might say, wow, how do you show this? It turns out it follows from Einstein's theory, but it actually follows again from continuity. So continuity proves this fact. It's quite remarkable. You might think 3, 5 images, this must be some deep property of Einstein theory. It just is fact, follows from continuity. And to see that, you consider that you have a star, red star, let's say here, and we are on the Earth looking at the star. So consider a sphere near the center of the star, centered at the star, and consider another sphere which is not centered at the, which is not centered here. So it's centered somewhere else, near the passing through the air somewhere. And so we are interested in trying to understand what happens to the light images. So suppose you have a light coming from one star going to the other. So it passes from the first sphere and it hits the other sphere. So the number of images that we have is certainly related. In this simple example you're saying is just 1. This is kind of clear from this picture, because every light ray which hits the first sphere hits the other one just straight ahead. Here I'm assuming that there is no matter. So if you have no matter between the star and the Earth that we are at, you just see a straight line going from each one. Is that clear? So in this case, it's boring. You just get 1 image. But what I wanted to use this to illustrate is that you get a map from a sphere, this blue sphere near this one, to this bigger sphere farther away. And this map is given by a fact that this light ray that goes from one, each point gets mapped to another point, from one point to its image. Is that clear? So we get 1 image in terms of this function. But there's a mathematical property called the degree of the map, and the net number of pre-images of a given point counted with a plus or minus sign is a constant. It's called the degree of a map. In other words, you look at each image and you look at how many points went to that point, you count them. It turns out that this number doesn't change by continuity. Of course, you have to count them with a plus or minus sign. And this number is called the degree of the map. So when there is no matter between the sun and the earth, the degree of the map I just defined is 1, because every point comes from one pre-image. And if you now put matter, suppose now you add matter and galaxies and all that, the degree of the map is still 1. So now you might have more than one pre-image, but the net number of pre-images must be 1 if you add it with a plus or minus sign. So this illustrates it here. Suppose this is the Earth, and we get no matter between them. So you get, and this, suppose that the center of this picture is where the star is. You get straight lines, so you get one image here. But suppose now you put some matter in the middle. So that has effectively, it turns out, changes the geometry of this map between the sphere that you have to the sphere that we are at. And if you compute it, depends on where you are, the degree of the map should still be 1, but it turns out the number of pre-images change. For example, if you're where the Earth is here, you only have one pre-image because there's only one place it hits here. But if you move the Earth further, for example, if you move it, well, here it's still one image, but if you move it further up, let's say a little here, now you see there are 3 points it cuts. And if you go further up, you get 5 points. So you always get an odd number because each time the thing goes, it folds back on itself, and that's the degree of the map. But it folds backwards, so the orientation has changed. So you always get even number of pluses and odd number of minuses. Half of this and half of them are minus, such that the net number is +1. So you have 3 pluses here and 2 minuses, so 3 minus 2 is 1. So the degree is always 1 in this example. And so this shows that in this case, for example, we have 5 images. Now I will give you the power of mathematical abstractions. I love ants. So this puzzle is about ants. We have 4 ants, which are moving on a plane, on a 2-dimensional plane. They are moving at constant velocity in different directions, not parallel to each other, in different directions, with different velocity, with constant velocities, but their speeds might be different, but each one goes with the same, with the constant velocity. So we have a situation like this. We have 4 ants moving around like this. And you see the ants are all colliding with each other, pairwise, except we don't know whether the last 2 ants, the 2 ants 1 and 2, do you think that they have to collide or not? So in other words, we are given 4 ants, which are moving at constant velocity, and we know that all pairs of ants actually, not only their paths cross, but they actually hit each other and cross. We just don't know whether ant number 1 and ant number 2 also cross or not. The question to you is, do you think that the ants 1 and 2 also have to cross or not? How many of you think they have to cross? Raise your hand. How many think it doesn't have to cross? Okay, so indeed, majority thought it had to cross, and let's see why. To do this, it's actually useful to abstract. So now the abstract map comes in. What is abstract to here? There's nothing to abstract, it seems boring. You have a plane, you have ants moving. What do you want? What is abstract about this? The abstraction is higher dimensions, like in string theory. Higher dimensions for ants on a plane? Are you serious? Yes, I am serious. But the extra dimension I'm bringing in is time. So now think about this in space-time. We have 2 spatial dimensions. This is the plane, but you also have time. Now, if the ants are going with constant velocity, their word line is a straight line in 2 + 1 dimensions, right? If the ants are going to collide and at the same time, that means that their word lines intersect in 2 + 1 dimension, in 3 dimensions. Is that clear? So now we have 4 lines. Each ant defines a straight line. And we know that each pair of lines crosses each other, except for one pair we don't know. Now I'm going to show you geometry, use Euclidean geometry to show that they have to cross also, just by basic Euclidean geometry. And to see that, you just, again, as I said, think about this in 2 + 1 dimension, and these ants, their word lines cross, and you see when they cross, they form planes. So here, what happens is that, let's look at these planes. So the ant number 2, let me go back here a little bit. So let's put it here. So look at the ant number 2. Ant number 2 has this word line, and ant number 4 has this word line, the yellow one. And the 2 and the 4 line, the lines 4 and 2 should cross. And the line 3, the ant number 3 also, we said, crosses 2 and 4. So therefore, since it crosses, the 2, 3, 4 forms a plane. So the plane 3, the line 3 should be on the same plane as the 2 and the 4 defines. So the lines 2, 3, and 4 lie on the same plane. For the same reason, the lines 1, 3, and 4 lie on the same plane. So both line 1 and line 2 lie on the same plane as defined by the 2 lines 3, 4. Now, we said that the ants don't move in the same direction, and the 1 and 2 are on the same plane. And since they are not parallel, because we said they are not in the same direction, they have to cross. That's it. So we are using simple topology and simple ideas from Euclidean geometry to answer this puzzle, but there was an abstraction. The abstraction was the extra dimension, time. So putting time into the discussion was helpful, and that's an example. Okay, the next thing is duality. Dualities have been discovered in string theory and other areas of physics to be extremely important. These duality symmetries are very powerful. And it basically means the following. Two seemingly different physical systems could nevertheless be identical, even though they look completely different. They could be part of the same physical system despite the appearance. Okay, so that is the surprise. So how could that happen? Well, first of all, we illustrated by a piece of art. So this is a drawing by Escher. You see, this is a beautiful drawing, but it illustrates the idea of duality very nicely. You see, if you're on the left upper corner of this drawing, you think that you are in a day in a sky, and you have these black birds moving to the left. On the other hand, if you go from the left part of this drawing to the right, you see that you are in a dark night situation where you have white birds moving to the right. If you go from up to down, you find that instead of the white birds, you have white fields, and instead of the black birds, you have black fields. And so this whole thing is actually fits together, and the duality in physics tells you that this whole thing fits together into one framework. And if somebody tells you this is a drawing of a day, somebody says, no, it's a drawing of a night. Or somebody says, no, it's a drawing about black birds. Somebody says, no, it's a drawing about white birds, and so forth. So everybody might disagree, but actually they're talking about the same drawing, but different parts of the drawing. And this is the structure of a lot of things we have found in duality symmetries in string theory. So here I'm going to give you a puzzle about dualities. Suppose you have 1 meter strict long, 1 meter. And again, let's go back to my favorite example of ants. We have 20 ants. 20 ants on a meter stick. And the ants, so the meter stick is 100 centimeters. And the ants are going with a constant speed, 1 centimeter per second. All of them have the same speed. They either go from left to right or right to left, 1 centimeter per second. Okay? Now, in other words, if you had just one ant, it would take 100 seconds to go from one end to the other. However, you have many ants on this meter stick, and the ants collide. So if 2 ants collide, they reverse direction and go back the opposite way with the same speed, and until they hit the next ant. And if they hit another ant, they go again back in the same, they reverse orientation direction again. Is it clear? So in other words, we have a situation like this. The ants are moving on a meter stick, and when they collide, they reverse direction. Like, for example, this orange one, it's the yellow one, and then hits direction back. And when they get to the end of the meter stick, they fall off. So the puzzle you have is that where do you put the ants, and which directions should they initially move so as to maximize the last ant, the time that the last ant is on the meter stick. You want to find the maximum time. So you have to design where do you put the ants so that you have a maximum amount of time. How many of you think you have to put ants near the middle somewhere? How many of you think it doesn't matter too much on that? How many of you think it only matters where you put one of the ants? Of course not. It should, well, most of you think, actually, except for 2 people, most of you thought that it's not possible. It should depend on all the ants. But actually, the 2 people who said no, it should only depend on one ant were the correct answer. It turns out only one ant will determine this. And this is duality symmetries. Why is it duality? What does this have to do with dualities? Well, the duality here is that I have here confused you by telling you that the ants have different colors, and the ants, when they collide, they reverse directions. Suppose I considered all the ants to be black. Then what does it look like? Well, it looks like the ants are colliding and reversing direction, but you don't know if they're actually reversing direction or they're going through each other. There is no difference. You couldn't tell. So by the duality transformation of converting identity of the ants when they collide, it doesn't make any difference if they collide or they pass through. And therefore, all that matters is that you put one ant at the left side and tell the ant go to the right. And it doesn't matter where you put all the rest of the ants. It takes 100 seconds. So here the duality symmetry comes to solve this problem in an elementary way. Is that clear? Okay, great. Finally, this is going to be my last puzzle. And I love this puzzle because it shows reflections of scientific methodology. When we tell how science works and how science is supposed to work, we always say, what do we say? We teach our students, science is like this. You take examples, which is the analog of experiments. You do experiments. Then you formulate a general principle based on these examples. So you have examples, you then look at the examples, you see some common features, you come up with basic principles. And then you come up with arguments, why those principles work. So you try to explain this, like Galileo tried to explain. Is that clear? So this is the methodology of science. But there's one important part which I haven't written down here. The important point is that you never stop experimenting. You always look for doubts. You always try to doubt yourself. That's how science is supposed to progress. So let me illustrate this puzzle. Suppose you have a circle, and your circle, this green disk here, and you put points, 2 yellow points here on the boundary of the circle, and then you connect them. And then you ask, how many regions do I get inside this circle? Well, in this case, it's kind of clear how many circles you get, how many regions we get. We get 2 regions. So in other words, when you put 2 points, you get 2 regions. Now, suppose you put 3 points. How many regions do you get now? Well, I'm putting 3 points, and then I ask how many regions I get. I get 4 regions, 1, 2, 3, 4. So in other words, with 2 points, I got 2 regions. 3 points gave me 4 regions. I'm putting these points on random positions. I'm not choosing any specific symmetric point or anything. Choosing generic random positions. Suppose I put 4 random positions and then connect them. How many regions do I get? Well, we just connect every point to every other point, and we just count. It's not difficult to see that we now get 8 regions. In other words, 4 points give you 4 regions, 3 points, 2 points, 2 regions, 3 points, 4 regions, 4 points, 8 regions. Do you see a pattern? Okay, now I want you to look at the next one. You add 1 more point. This is 5 points. How many regions do you think we should get? How many think it's 16? Raise your hands. Oh, wow. Okay, I thought it's almost obvious, but okay. So if you take 5 points, you get 16 regions, right? What's happening here? It is doubling each time, right? Can anyone tell me why it's doubling? Well, let me say one idea that one might have. if you connect every point to every other point, each region is either it's to the left or to the right of that region. So each time you introduce one extra point, each region is divided by multiplied by a factor of 2 because it could be left or right. So it should be multiplied by a factor of 2, obviously. Okay, this is the argument. Explains, so we now have a fundamental principle. The formula of the number of regions is 2 to the number of points minus 1. That's the fundamental formula. So, but experiment has to continue. Science has to continue. So the next number is 6 points. How many think what the answer is going to be for 6 points? How many think it's going to be 32? Raise your hands. Well, let's see. 1, 2, 3, 4, 5, 6. Oh, looks like 31. What happened? 31? I thought we gave an argument. We had a general principle. What happened? It was wrong. It is 31. It is 31. We just made a wrong principle. We thought we had figured it out, but experiments showed us we are wrong. And so we have to go back to the scratch board and figure out what was wrong. So the number of regions is 31. And I did not put points in funny places. I'm putting generic points. You can draw for yourself any configurations you want, generic one. Don't pick points in a special symmetric point or anything. Just choose random 6 points. You will find 31 regions. It's going to be laborious to count them, but it's 31. So this already shows to you that we got an intuition which was false. The factor of 2 by experiment, and in fact, even the theoretical explanation I offered to you was wrong. But we corrected it. Well, we have to correct it because the experiment tells you the answer is 31. And indeed, the general formula turns out to be, if you have n points, the number of regions you get is 1 plus n choose 2 plus n choose 4. It's polynomial in n, not exponential. So I will leave it to you to check this formula. So in fact, if you have, for example, 7 points, instead of 64, you get 57. So let me say that I hope I have conveyed the power of simple mathematical ideas in the context of physics. Even the most complicated ideas in string theory have simple illustration in the context of mathematical puzzles. And we should not be shy from learning about math and applying them into the physical realities. And again, thanks for listening to my talk. So let me try to unshare my screen. And I unshared my screen. I welcome any questions you have.
Thank you very much for this nice and very exciting talk.
Thank you for listening. I'm happy to take any questions.
Yes, please ask questions.
You can unmute yourself and ask questions. There's no reason to write in the chat. So please feel free to unmute yourself. I assume everybody can unmute them. So right, okay, I think people can. Yes, please go ahead. Yes.
Okay, thank you for the presentation. I'm wondering, you have on one of the slides related with this Earth and the equator, at the last slide you said that there would be 2 different points next to each other with the same pressure and temperature, right?
Opposite to each other, yes.
Opposite, okay.
Yes.
So last week we had an earthquake.
Yes, I unfortunately heard about it. I'm very sorry to hear that, yes.
Okay, so I'm just thinking loudly. If an earthquake can change the pressure at that point on Earth, would it have another point on Earth that would change the pressure as a result?
Yes, if you measure the vibrations on the whole Earth, there will be 2 points which have the same amplitudes.
So could we say that?
But not necessarily where the earthquake was. Somewhere, the place
somewhere.
is not somewhere. Yeah, 2 pairs opposite each other.
Directly 180 degrees at the other direction.
Exactly. Opposite right to the center of the Earth. Yes.
So
by continuity.
By continuity. So the last week's earthquake created some change at the
It created
other
some
part.
vibrations, and so the amplitude of the vibration, if you think about the amplitude of the vibration, yes.
Okay, okay.
So
Thank you very much.
It's that kind of powerful things. The continuity is already powerful.
Okay, thank you very much.
Other questions, please. Yes, please, Berke.
Why two opposite points, same temperature?
Why two opposite points have the same temperature?
Mm-hmm.
So that was continuity explains it. So in other words, suppose again, let me explain it again. Suppose you have a circle. Suppose you're at one point of the circle and the other point opposite to it. Suppose one side has higher than the other one. Now, if you go all the way to the other side, then that point is going to be lower than the other one because you went from higher to the lower. But something which is higher in one case gradually goes to something which is lower, has to cross a place which is zero, which is equal. So continuity tells you the higher cannot go to lower without crossing zero, and that at that point when it crosses, it's equal temperature. Any other questions?
Thank you.
Yes. Anyone? I don't see a hand. Does anybody want to? Yes, I see Alkan.
Can you hear me?
I can't hear you, Alkan.
Okay.
Could you please speak
Can
louder?
you hear me now?
Just barely. If you can speak a bit louder, I can hear you better.
Okay. I'll do my best. Thank you for this very nice talk, Professor Vafa. I have a question about symmetry of living organisms that you briefly mentioned. There's also this left-right symmetry that is very common in us and most animals. Can you hear me?
Yes, I can see. You're saying there's
Okay.
something symmetry common between us and many animals?
No. I mean the left-right symmetry of the body.
Right.
Yes. And one argument for it that I have heard is locomotion. This left-right symmetry allows us, to move more effectively. I was wondering if you know any other good reason or have you heard anything else about this subject?
I have not studied this subject. I think it's certainly interesting to study it. So I don't have anything to offer. It's just there's an approximate left-right symmetry, clearly, but I don't know a good explanation. And it's not exact, as we know.
Yes, definitely.
I don't have.
Thank yeah. Okay.
But there must be a reason. Yes. Any other questions? And you're also welcome to unmute yourself if I don't get it. Umut, please go ahead.
Thank you first about your presentation. I want to ask you, other than learning the physics subjects and solving problems about that subjects, what can we do to improve or puzzle solving, problem solving abilities?
I think the best thing is just to study and, right now the great thing is that there are a huge amount of resources available to everybody in the world. So you in Turkey have a lot of resources available to you. And so I think just studying and reading and, working through things, going to university, learning the subjects and so on, and continuing working afterwards is the only way I know. There's no shortcut. You see, a lot of people think that, the ones who are not familiar with science think that maybe there's a shortcut. That, if I just suddenly do some magical thing, I can get the answer without going through the hard work. I often get letters or emails from people who often say, I have proven Einstein theory is wrong. I have found the right theory of quantum mechanics. I have do this. And then when you ask them, how did they come up with this? They say, well, I have been thinking about this by myself, and the argument are this and that. And then You ask them, well, have you read any of these books, what Einstein said in details? No, he's wrong anyhow. This is the right thing, I'm going to tell you. So the problem is that, so that is the big difficulty. So it's easy, they think it's easier just to come up with a theory, forget about learning what has been done. And that's unfortunately a big mistake. And of course, it takes a lot of effort to learn what has been done through centuries of hard work by brilliant people and people, you know, Einstein, Newton, Feynman, others. So of course we have to learn. So my advice to you is study, learn, and then don't stop doing that, and then contribute. In other words, after this learning, you're in a position to have, after you master what has been done, don't think that you have anything missing. In other words, don't feel that you're not in a position to be able to change the world. You could be the next Einstein. You should feel that you can be the next Einstein. Don't feel like you're underprivileged because of this or that. You have all the resources available for you. An example of it I would always give is Ramanujan from India. He had no resources really, and he got such a prominence in mathematics. So I think there is no boundary. Right now, internet and all that is so amazingly available that, and not to mention all these beautiful, fantastic universities and faculty and all that there's no reason not to be able to take advantage of resources available. And I would encourage you to take advantage of all these resources. But hard work is the key.
Thank you.
Yes, Alina, sorry.
Yeah, Alina, it's not a problem. So if you like remember the sphere that you showed us, the same temperature and the same pressure.
Yes.
So can we think that our universe is like that sphere? So can we say that like everything has their own symmetrical thing to balance, or?
Unsymmetrical things to balance, you mean the temperature and pressures being equal? Yes, so there's here, all I'm using really is just continuity. There's no balancing. I wasn't saying that it's this balance between temperature and pressure is there to maintain some order. Not really. It just was, in some sense, I was just trying to say it's a kind of a trivial statement following from continuity. So it's not deep in that sense, other than appearing to be deep. It appears to be deep, but it's just continuity, nothing more. So that was my point here. That is, sometimes we think that what we are saying is something deep, but actually it's just one little principle. Of course, that principle is important, and that could be just the simple principle of continuity. So that was the illustration. There's nothing more than that for that.
Okay, thank you. But also, doesn't the string theory also, in a kind of a way, explains the parallel universes?
So in string theory, you can have what's called landscape of solutions. So you have a huge number of solutions, and we seem to be in one of them. So you could call them parallel universes or whatnot, but yes, there is a possibility of having many, many different universes around, possible universes. There's this other parallel universe which has to do with the notion of quantum mechanics, with the notion of parallel universes as an interpretation of quantum mechanics, which I don't know if it's any relation between this and that, but at any rate, one basic feature we have learned in string theory is that you can have a huge number of possible universes. You could have had a universe with different number of particles, different mass spectra, different forces, all that. So we happen to be in one of them, and nothing is sacred about our universe. Nothing is that special about our universe. And so in some sense, we have to understand what it is that our universe is made of and so forth, but we have to take it in mind that these are only just examples of all possible universes that could exist. And indeed, we believe that our universe is going to decay away, and therefore it's going to go to some of the other universes. So we know that this is not going to be forever. So our universe has a possible lifetime. We don't know exactly what it is. Some people like myself estimated maybe it's under a couple trillion years, but we don't know exactly. At any rate, we do believe that the universe is going to go to these other ones, if you want to call them parallel or whatnot.
Thank you so much.
Well,
have a nice day.
Good. Any other questions? Yes, Denizcan.
My teacher.
So thank you, first of all, for your awesome presentation.
Thank you.
I follow a physicist on YouTube. I didn't read her books, but Sabine Hosenhoff has an idea that the search for beauty or seeking beauty leads physics astray in general. I can't really explain her idea very well, but well, I have two questions in mind, and I think they are related. Like, I want to ask if you think that math is a kind of language of the universe, or it is in the center of all physical reality. It should explain, it should somehow be able to explain everything, or, and one question, and other question is that are we somehow trying to seek beauty when we try to fit all data in somehow a mathematical model that is the most simplest or the most beautiful we can?
Yes, I think there's a famous statement by mathematician Hardy, in fact, collaborator of Ramanujan, that there is no permanent place for ugly mathematics. That always only beautiful things, even in mathematics, last. The same applies, I think, to physics, that there's physics, only beautiful principles last. You could have some, approximate description of this and that, but ultimately things are settled in a beautiful way. Now, coming to your question about why does it have to be mathematics? Does it have to be beautiful mathematics that underlies physics? We just a priori don't know it had to be or not, but to me, what is unavoidable is that physics should be logically consistent, right? We cannot say two things which are contradictory, right? That's just pure logic. Mathematics, in a sense, is the totality of all logically consistent structures. So whatever we say in physics better fit in some form of math. That's for sure. Now, it could be that the deep principle of physics is not a complicated piece of math. It could be a very boring math, but it's still logical. Or it could be that the simple principle of physics is a deep part of math. I'll give you an example. Einstein's theory of relativity, special relativity. It's remarkable. The fact that time is relative and all that. If you translate to mathematics, it's a boring linear algebra, totally boring. Okay, it's a transformation, it's a linear transformation of x, y, z, and t, and it gives you another x, y, z, t. A mathematician might say, so what? It's boring, it's totally boring. But physically, it's beautiful and so on. So you might say that's an example. That means might say beautiful principle of physics becomes boring math. Okay, you could say that. It's still logically consistent math. There's nothing inconsistent with that description. So it is true that not every beautiful principle of physics have to be a complicated, beautiful principle of mathematics. That doesn't have to be. Example is this Einstein theory of relativity. Or some of the puzzles I try to raise is that simple ideas of math could be important in very deep ideas in physics. Could be. So that's the relation. So my view is that math is a useful language to describe science and physics in particular. And therefore, why not use elegant ideas in math to describe elegant ideas in physics? However, we cannot say just because the idea is elegant in math, it has to be good in physics. That we don't know, and vice versa. So one thing that I was learning when I was a graduate student in physics is to be careful about math. Don't think everything good in math has to be in physics. And so, in other words, you could go astray if you push everything that you say, I don't care about physics, I just want to learn math. And just because math is good and everything is math anyhow, so why don't I bother? That attitude I disagree with. So math is elegant, but you have to use it when you really need it, but you have to be aware of it for sure. So that's my view. Knowledge of math is important. Pushing it to be used is not necessarily correct. You just have to be ready to use it and welcome using it because that's the language of nature. Any other questions?
Hello.
Hello.
I wonder about the core philosophy behind the physics, all physics. As far as I can see, it's about relations, as the smallest particles like quarks, for example, the gluons, the messenger particles, all do the work.
So you're asking whether things are related to each other? I didn't quite completely understand your question. Sorry, can you repeat your question?
Pardon?
I did not understand the question clearly. Can you please repeat your question?
As far as I can see, everything in the universe is related to each other. For example, the gluons, the small particles in subatomic scale, all do the communications between other quarks.
Yes. So it turns out that indeed what you're saying is correct. Everything is related to each other. In the context of string theory, there's a unification of all the particles to string. So a different vibrational mode of string or different configuration of a string gives you different particle. One of them is photon, one of them is electron, one of them is a quark, one of them is graviton. So there's a unification into one object, string. So that's one of the elegant things about string theory, which is kind of unifies all of the forces and particles into one entity, and that entity is strings.
And there is M theory. Did you hear about it?
Yes. Yes. Yeah, this is related to string theory. M theory is the same as string theory. So I talked about that in my talk.
Thanks.
You're welcome.
Thank you.
Any other questions, please?
Thank you very much for your very nice presentation, interactive presentation. And we hope we can see you in our seminars in Turkey again.
Thank you very much, Koksal. It was a pleasure to give a talk here, and thanks for suggesting it. I think it was your suggestion that Alikram has followed, and I was able to give a talk. It's a great experience to talk with Turkish students and colleagues, and I really also wish I could be able to visit there. Hopefully soon.
We hope.
Thank you.
Thank you.
Any other questions? Okay, I don't see any more questions, Alikram.
If no more questions, perhaps we can stop here. What do you think?
Sounds great. I wish you guys all safety
once again.
Situation, and I hope everybody keeps safe and continue doing good work. Science and puzzles are fun, so that's one way of spending time, but also research is a good idea. At any rate, it was a great pleasure giving a talk here for you guys.
Thank you so much. It was an honor for us.
Thank you very much.
And we hope we will see you here in person.
Thank you.
In the near future.
Take care, everybody.
Yeah.
Bye-bye.
Bye.